Thanks, Earl, Paul, and the gang for inviting me and for giving ECP, a forum here to give updates. We're going to have, I think, a few other speakers that I'll note. So Andrew talked about applications, and I'll hit that a little bit as well. But I think this will be a complimentary update. For today's update, a reminder of who we are. Most people probably know. I certainly haven't forgotten, but I'll mention that. Bottom line up front, kind of what we've done the past, since I've been back here. We've gone through what we call a final design, and this sounds a little strange because we have four more years yet to go. So, in our mind, it's not necessarily final, but we set our performance baseline. It's very important. Quick look in the rearview mirror, kind of where we've been. On the app side, I hope you would agree from what Andrew showed, we've made great progress, and we've got some computational hurdles now that I think are becoming more clear with knowledge of the coming systems. I want to talk in particular about our approach on computational motifs, really paying off, and I'll give you a few examples. And then integration, really within ECP, it's a very complicated project. Our software technology and application efforts, I think we're doing a better job in integrating them and working harder with the DOE facilities. And then a look ahead. Apologies, I really like this down here, so I'm just looking at that. So apologies. So a reminder, we're part of the Exascale Computing Initiative. There are three first mover procurement projects that are one at Argonne, Oak Ridge, and Livermore. And Livermore, they're outside of ECP, but critical for our success. In fact, these systems are on our critical path with regard to deploying applications, our software stack, and making sure that we deliver on our performance parameters. And so we are a piece of the ECP pie. I will also note, Thomas Schultes mentioned, there's a special issue in computing and science engineering where myself, Stephen Lee, former ECP deputy, now retired, and Irene Qualters, NSF, now at LLNL, wrote, give you a more detailed overview. So you can go look at that article for more detail. And again, we're broken really into applications and software technologies and integrating into facilities. Just as a reminder, as Andrew mentioned, we have 24 first mover applications, 3 of them are national security, and the other 21 I'll briefly mention. I'm not going to run through them like Andrew did. We have 67 products that we've really worked hard to push out online, and I'll say a little bit about that. And then I won't focus on path forward so much this time, but talk a little bit about how we're working with the 3 facilities in the Office of Science, NERSC, OLCF, and ALCF to really performance engineer and tune our applications. That process is moving ahead full steam. I usually don't show org charts, but I realize I don't really acknowledge like I should. Barb Helen and Took Hong are our program managers in the Department of Energy, and Dan Hogue is my federal project director, and they're really critical for our success. We've enjoyed a lot of support and tough love, I guess I would say, from our DOE sponsors, so I need to point that out more. I circled Andrew Siegel's name, and I forgot to circle Al Geist's name because we have 2 speakers here today. Al's our Chief Technology Officer, and Andrew Siegel directs our applications. I'll also note that Dave Martin and Susie Titchener, who are here, are co-executive directors of our industry council. We don't mention that very often. Julia White is here in our technical operations, and I believe Nick Romero is going to talk about one of our applications later this afternoon. And so we do have some presence here. And Mike Bernhardt is our communications director. Mike's in the back there. So I probably missed some folks, but I just wanted to point out that there's a lot of presence here at these meetings. They're a great venue. So what is our final design? Well, a DOE requirement, which is painful but yet very useful for us, is to really set a baseline before we go into what's called critical decision 2. Everything we do seems to be critical, but we have these very formal critical decisions, and we went through a really tough owner's review end of June, and that was a really comprehensive scrutiny of how we're organized, what does our 4-year plan look like, and our management processes. And as a result of that, we scrubbed ourselves and got scrubbed pretty well, and have a pretty good feeling for what lies ahead, at least in terms of known unknowns. So again, we set what's called our baseline. I'll say a little bit more about that, sort of the next 4 years. We now know more about schedules and technology targets for the 3 first mover systems. That's fantastic. I would say most of the unknown unknowns are gone. Now there are known unknowns. We've set up shared milestone plans with DOE HPC facilities. As hardware rolls in, as software stacks are being developed by the vendors, we need to be joined at the hip with those activities. That's been a contact sport, taking a lot of give and take and a lot of meetings and interactions, and we feel pretty good about that. I mentioned the fact that we have known unknowns remains, and one really just, we really are after a robust, portable performance accelerator programming model. And as Andrew mentioned before, Kothe and Raja, these abstraction layers are evolving and growing and you know, undergoing more and more adoption. And so we're not surprised there, and I'll say a little bit more about kind of what we see moving forward. Our AI ML scope is we think cutting edge and impactful. Rick, I missed Rick's talk this morning. I heard it was pretty entertaining, not surprising. He leads our Candle effort. So he's really an exemplar for the AI supported effort in ECP and XLearn, but we will see this likely expand as we retire risks going in, moving in forward in the next 4 years. The DOE just 4 days ago announced an AI and technology office, and that's an important development for us, and so we want to see ourselves really develop a wedge in this space and a springboard for beyond ECP in this technology space. In terms of where we've been, kind of hardware and integration, path forward elements paying dividends. We've seen that directly in the procurement offerings, and that program continues at least for another year. And we're focusing now on really deploying our software stack and version 0.2. So I guess Mike Caru's not going to get to 1 until he feels like everything's there, but version 0.2 is out there online. You can find it. And we're really starting to tune applications now. And Andrew gave a great example, the Exalt application, seeing almost 90x performance improvement over the 3 years. And there are some really good people at NERSC, and part of the ECP project, that really worked hard to make that happen. So it's been a really nice co-design effort. Software technologies, again, we're deploying our extreme scale software stack. We have decided to, not surprisingly, have increased focus on mixed reduced precision and these abstraction layers like COCOS, and PGAS efforts like UPC and UPC++ we see growing as well. So we're working on growing some of those areas moving forward. In applications, skin in the game, quantitative criteria, that's tough 4 years in advance to commit to certain challenge problems with certain specs and certain performance. And that's what our baseline, setting our baseline really means. So we've been working hard, kind of moving forward, but I put this slide together when we went through our final design, and so we've been, even though our application and software teams weren't funded fully until FY17, so the past 3 years, some of us were working along with DOE and putting together our project office, getting the RFIs out, getting our project office established, mission needs statement. So I don't think people appreciate, maybe you do, that there's a fair amount of work just to get a large project stood up. So we're well past startup. Final design really means we feel pretty good about where we're headed, we feel good about our plans, and we feel good about committing to certain performance metrics. So we went through that review in June, and Lori Dyson, who's not here, did a great job in sort of driving this process on behalf of the project. She really drove the whole design, working with the leadership team and our principal investigators. We have 80 of them. And so she's no longer new to the project. She jumped into the deep end and really did much more than tread water. And you know, our final design, you know, if you can think about sort of relative to a building, it's not really a blueprint, but yet it is. But this is the way we view our final design, is how are we structured to succeed. And then probably the one I put in bold that most people would resonate with are our technical plans. How are we defining what does success look like Andrew said, what we're calling key performance parameters. What are our plans over the next 4 years? They have to be flexible given their risks, given this is R&D, and yet have to make commitments. And where we depend on each other and others. So that essentially was a tough review, and we got through it very successfully, in large part due to Lori's efforts, who was unable to attend, but I wanted to call attention to her efforts. Andrew mentioned all the apps. Okay, I'm just going to put this in for a leave behind, but you know, it's quite a portfolio that we're committing to and taking into this sort of next baseline period of 4 years. I'm not going to go through all this, but I thought it'd also be good leave behind. When we sat down with the applications, we talked to them about what are your hurdles, and I've got a mix here of hurdles and cool stuff, so they're not really hurdles, but you can see. Let me take fossil energy, for example. So here we've got AMR, EB as embedded boundaries. Sorry, I resisted the temptation to go really small font, lots of words. That's a weakness of mine. So AMR plus embedded boundaries plus discrete elements plus multi-phase incompressible flow. That's hard enough from an algorithm and but much less a software point of view on an Exascale system. And so each one of these has challenge problems, and in our final design, these challenge problems map to a very explicit, here's an initial condition, here's a boundary condition, here's how many degrees of freedom I'm going to solve. We're not claiming we're going to solve these problems. We're going to have the technology to address the problems directly in a defensible way. So this is what kind of thing we went through in our final design, is nail down your challenge problem. And again, the expectation here is the applications will not be boutique. They're not going to just run on Exascale, and they're not going to just do this problem. But to have specific challenge problems and targets, we can really drive the performance, drive the plan and measure the plan, and make sure every one of these problems was negotiated with DOE program office. So they're all very, very high priority problems. Andrew mentioned the EXALT project. That's extreme materials. So that's accelerated MD with replica dynamics. It's also on-the-fly quantum-based potentials. It's a real poster child for maybe where machine learning can help, and Andrew showed that. So just some examples here of the kinds of hurdles that the apps are dealing with. Again, this sort of rounds out the list. I haven't included the national security apps that have tremendous challenges and computational hurdles that they are overcoming. But here, Thomas Schultes talked about climate modeling the Earth system, and Nick Romero will talk about that later. But you see there, the goal there is 5 simulated years per day, which is pretty onerous. But with a multi-modeling framework approach to be able to get cloud resolving physics put in. So in any case, I'm going to take you through a few examples and focus more on how co-design has helped these efforts and how software technology has helped the efforts. So co-design is really kind of misnamed because we really kind of view ourselves as co-designing everywhere. These probably should be called co-design computational motifs, because we looked at the applications and there's order 12 or 13 motifs that are common to almost all of our applications, and that's basically we're defining a motif as a common pattern of communication and computation. And you see the 6 centers we have below that really were driven by our needs of our applications. And each co-design center really kind of has a couple of motifs. For example, SEED, Zanio Kolep leads that, Lawrence Livermore is doing great, and it's unstructured mesh. There's a lot of gather, scatter, indirect addressing. There's a lot of finite element basis operations. There's a lot of dense local linear algebra. So it's really kind of several motifs in one. So we are seeing this approach really work because applications, and we haven't forced it, we thought about it, but we haven't had to, and that applications are in fact adopting these motifs and the co-design centers. So the co-design centers aren't just emitting concepts and best practices, they're full of those, but they're emitting software. And so we're seeing what I think are next generation community packages that really in many cases did not exist. So these are kind of a higher level middleware layer that apps can sit on now and really be able to focus on the physics and have a lot of this tough effort, but still bookkeeping effort, go on behind the covers, underneath the covers here. So we're seeing lots of applications within ECP adopt these co-design center technologies. So when a particle center was first proposed, I forgot what their name was. I didn't like it, and I said, come up with a better name. So they came up with COPA. So naturally, your library would be called Cabana. Now, I'm actually a Barry Manilow fan, so is my wife. So, and this is a young guy, everybody's young to me, Stuart Slattery at Oak Ridge, that probably, I think he's heard of Barry Manilow, but in any case, this has been a nice development. So, you see a nice chart here that shows molecular dynamics relies on particles, long-range, short-range particle and cell. And a missing piece is SPH, in-body quantum. So again, here's a chance to really make an impact by focusing on how do we push particles, how we map particles to mesh to particles, etc. And so there's been a really nice development in terms of a Cabana library. And the neat thing about this is Stuart sat down and he came up with an array of structs of arrays, or AOSOA, that really did implement well on GPUs and commodity cores. And it's shown down there on the bottom. And then did a native CUDA implementation. But then thought, well, what the heck, I'll try Cocos. He brought Cocos in and it did almost as well. So he's actually adopted Cocos as one of his lower level layers. And so the Cabana library builds directly on Cocos, and so that's a nice feature. He didn't plan for that, but he saw that this abstraction layer that comes out of Sandia really helped him reduce his effort. And again, in bold here, we have a lot of Fortran code, and it's very important for us. It's not just legacy code. And Andrew mentioned about a third of the apps. The XGC code, which is an important fusion application by C.S. Chang at Princeton, is predominantly Fortran, and he was having trouble getting good performance and porting, and actually found that there was times he couldn't run on Summit because of compiler challenges. Brought in Kibana as the ion push and now the electron push, and first thing Kibana allowed him to do was to actually run on all these machines. And it's interesting because his code calls Kibana, and then underneath the covers Kibana can call Fortran kernels, and that's what's shown there. So that's nice because we have now an abstraction layer written in C++, naming Kibana, that can help Fortran codes. And what they saw was the Cocos version gave them about a 10% reduction in runtime for a huge code just out of the box, and allowed them to now run on Summit, Perlmutter, and soon Aurora, Frontier, and Post-K. And so this is a large application that's many years old, and I never thought they would rip out the particle pieces, and they did, and they've adopted COPA, and that is really a big success story for for one of our co-design centers. XLearn we started about a year ago. It's the youngest of our 6 centers, and here's a recent success story, which is there's a lot of low-hanging fruit, I think, with machine learning and science, and this is not an Exascale driver problem, but I think it's an important one to bring out, because the XLearn Co-Design Center is really targeting facilities for a lot of the problems they're going after. In this case, is neutron diffraction of perovskites, which are viewed as kind of the holy grail or next generation photovoltaic materials. They're calcium titanium oxides, and they have certain signatures in neutron diffraction, as shown down there in the bottom right. And they're able to train a network to recognize the signatures, or recognize what signatures map to what structure. And so now they're able to use a trained net to sort of quickly move through design space. Or an inverse problem is, given a diffraction pattern, what is the material? And so I want to point out that a lot of what we're doing, or at least some of what we're doing, certainly in XLearn, isn't just everything at Exascale. We're trying to make a difference now, and we've been given direct guidance from DOE to really target our facilities, which are multi-billion-dollar facilities, neutron and light source facilities, as an example, throughout the complex. Here's an example of all the potential in light sources from Frank Alexander. He leads our XLearn effort. There are some that are Exascale class problems and some that are not, but yet still very important. One interesting one is in the case of LCLS, which is a linear free electron based light source at SLAC, is the beam may actually miss the target, the sample. The samples are dropping very rapidly in front of the beam, and they want to be able to quickly determine which diffraction patterns were misses, which diffraction patterns actually had 2 samples, not 1. And they can throw away a lot of data and really reduce the data processing requirements just by having a trained network that can say nope, 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 yes, yes. So this is an interesting area where we can come in and help. I can get more return and more productivity from light sources. And so I think this is a good example of, there are many light sources in the DOE complex and neutron sources as well, where machine learning can really make an impact in areas where we haven't thought about before. Let me move on to software technology led by Mike Aru. Mike's been here, I know, talking about his efforts, and he's really done a great job, along with Jonathan Carter, in productizing our efforts, still maintaining that higher risk R&D is going to give impact, but really working to productize what we're doing. And so, again, he's broken up his area into programming models and runtimes, development tools, math libraries, data, and viz, and you can see it there. But I also want to mention that about every 6 months he puts out the new comprehensive report on essentially what is going on in the software stack. And I put the link down there. It's on our website. He calls it this CAR report, Capability Assessment Report. So I encourage folks to go look, because there's kind of the 35 or so projects, order 5 to 10 page write-up on each project. So it's really a nice comprehensive report. And this gives you an example of the breadth of what's going on, and just sort of point out a few areas where we're seeing, we're seeing good return in virtually all the areas, but areas where we're going to put more resources in moving forward. Cocos and Raja, these abstraction layers are being adopted by applications. So we're going to see more adoption, and we're going to do a deeper dive and accelerate development there. LLVM, the previous speaker just talked about it, is very important for us for Fortran codes. The flying effort, well, was a F-18, now flying in large part due to NVIDIA. We're going to continue to fund that effort to make sure that we have a viable Fortran front end. We're also going to invest more in our math libraries in reduced and mixed precision. Jack Don's work with Nick Hyam at Manchester and Aaron Carson really opened a lot of eyes, myself notwithstanding, about how we can get a lot of return on essentially black box linear libraries by going after mixed precision. And again, we might be able to cheat and not have full precision, but what Jack has shown is we can have iterative refinement and be able to get 64-bit precision if we want with less precision. So we are kind of putting more investment and by doing it in math libraries, we think we can cross-cut across a lot of applications. FFTs are important too. I haven't mentioned that in the past. We have 2 efforts in FFTs that are really important for us moving forward. So that's another computational motif. Again, SDKs, I won't belabor it, software development kits, really a nice vehicle in place for packaging software. It allows ECP to interact with vendors and international communities. If you're willing to sign up to certain policies, you can contribute your package to a given SDK. The one that's most mature is our math SDK called XSDK. I believe there's 9 or 10 different math library options in there. And as an application person myself, that really gives you a very nice, almost plug-and-play capability to pit 2 solver libraries against one another. And we saw that in the WIN project where they said this multi-grid is not working well enough. We want to try another multi-grid. And these SDKs allow this more seamless trying different solvers. And this is all packaged together in what Mike calls the E4S. And you can see at the website there that we have a version .2 there with 37 products, so we're not quite up to our full product portfolio. One of the real important sort of risks that I think we're managing well is the interdependencies within ECP as well as within facilities. So apologies for the acronyms here, but AD is application development, ST is software technology, and HI is hardware and integration. And so we have these 2-on-2 or 3-on-3 sort of interactions and dependencies that I think a few years ago we felt like was kind of the single biggest risk for the project, but I feel like we've got a pretty good handle on this, and we're moving forward in terms of making sure that these interdependencies are understood. Now, Eric Drager at Livermore did this analysis where he looked at several SD products and then how they interact with AD products, and we call it the hairball. A little scary. And we found when we talked to the applications teams, they said, well, we use these sets of software. We talked to the software teams and they go, these apps depend on us, and those 2 answers weren't consistent. So we finally got real and sat down and created a database. And I put down in bold, I'm not sure that's ever been done, where as an application person I might say, yeah, I use this, this, and this, and the ground truth is runtime analysis. So we've got a interdependency database set up now, and I think it's going to let us track these interdependencies. And we have them mapped into critical dependencies, sort of backup dependencies, and then nice to have. This is important for us. We got to make sure for every app that rolls on the system, we understand the software stack pieces it's dependent on, and that they come along not for the ride, but they're there first and performant. And so we've worked hard. And I'll give you some examples of where we're seeing this nice synergy, just by putting a bunch of good PIs together and letting them work together and frankly one-up themselves has been really, really nice. QMC Pack, and I'm just going to focus on the red bars here, the red squares. QMC Pack led by Paul Kent. He was a little reticent bringing in Cocos. Thought it was going to be a heavy lift, was a little bit cynical about it. After sort of a 3 to 6 month period, it's not plug and play. It's not necessarily an overnight thing to bring Cocos in. Really found that it met his needs, and he adopted it as an abstraction layer. And the solve effort led by Barbara Chapman is really focused on the OpenMP aspects. And so what he's seeing now is ability to be able to begin to break up and parallelize his Monte Carlo Markov chain. And so I show other examples, and I apologize, but every project has a name. Like the Slate project is Jack Dongira. Okay, an Alexa project is led at Oak Ridge, and that's a data coupling project. So we're naming project to project, and you'll find these names in that big document if you want to download it. Other examples, and again, CD is co-design. So The WDM app is the whole device modeling fusion application. I didn't mention it, but here you've got a real research problem that they've overcome, and that's coupling a stochastic code, which is in this case XGC, with a continuum code, in this case gene. These are two gyrokinetic codes. One is really optimal for the inner part of the eater plasma. One is an edge plasma, so we got to couple them together to do the full inner plasma. And Adios is a framework by Scott Klasky at Oak Ridge that put together a nice way to couple these codes. And the framework is called the Kitty framework, and allows the coupling. So that was a nice interaction. I don't believe the WDM app team would have been able to pull this off as cleanly and as quickly as they have without this coupling framework. So Adios is not just I/O in this example. EQSIM Raja, Andrew may have mentioned this. I know we mentioned it in the past, but EQSIM is an earthquake risk assessment code. So it's a seismic wave propagation code, SW4 out of Livermore, coupled to structural mechanics code, Nevada, doing risk assessment in the Bay Area. They did a NADA CUDA implementation, and then Raja is another extraction layer, a little like Cocoa, it's a little more lighter weight, developed at Livermore, and they brought in Raja and found that they were able to get almost the same performance as CUDA. So they've adopted this extraction layer instead of going with native CUDA. So that's been a nice, giving them a nice edge to move forward more aggressively on the physics, knowing that this abstraction layer is there for them. My last example, not surprisingly, is Candle and XLearn, and here each project is working with each other. It's very highly synergistic, as noted there in that first bullet. And so the Candle benchmarks and the Candle environment really has helped XLearn get a jump start on surrogates. The surrogates are really important for uncertainty quantification and sensitivity analysis. In other words, you might have a multi-million parameter system like a nuclear reactor, Andrew talked about, and you need to be able to do sensitivity and uncertainty analysis, and you can't do that. We don't have a scalable UQ solution right now. But with surrogates, if you can reduce the parameters that define your simulation to a dozen or so, now you can do pretty comprehensive UQ and sensitivity analysis. So Candle's been able to really give XLearn kind of a jump start towards moving towards surrogates as just one example. So that is an interaction and integration effort that's not very surprising given the scope. The last thing I want to mention is the hardware and integration effort, and the path forward has been a really important part of this effort. But Terry Quinn and company have really stood up, kind of followed best practice from our facilities, which is an area called application readiness. And there are performance engineers and scientific computing people sitting in the facilities, NERSC, in this case OLCF and ALCF. This is their job, and they're used to doing it, and they like it. It's work closely with vendors to take an application and really take it down to the metal and performance tune it. And so we are funding these application readiness experts at the 3 facilities and selectively bringing our codes on board. And we're not waiting till Exascale, we're doing it now. And as I mentioned, this has really borne fruit already with the Exalt application at NERSC. And so this has really kind of taken the applications across the finish line. In terms of the road ahead, lots of reviews. These are painful. This is my last slide. These are painful, but necessary. And again, our target for completion is FY23. I have put in italics. We have some working dates on when we can get access to various early hardware or full system. And again, this required working very closely with the Aurora and Frontier projects. And for us, the ground truth is going to be getting on early hardware and really making sure that the experiences we've had, say on Summit, are going to bear fruit. We feel confident there, but we're not going to really check that box until we get on this hardware. We see that coming in the next year. So that said, thanks for your time and attention. I'll stop there.
Thanks, Doug. Nice presentation. I'm wondering if you have any vision of containers for high-performance computing going into the future.
We do. I hesitate because I'm not the person with that vision, but I will say that our SDK release at E4S are containerized in 4 different containers. I'm not sure that the DOE folks or the folks in ECP are going to agree on or decide upon where to converge there. But we have Charlie Cloud, Singularity, Docker, and what's the last one? Al, help me out. There's a 4th. Kubernetes. Yes, so we are aggressively pursuing it and deploying our software that way. I think you'll see that happen more with applications as well.
We're exploring Singularity at Lawrence Livermore because it uncovers the native MPI, which is important to our hardware-bound systems over there.
Good to know. Thanks.